Next, we take a look at non-differentiable optimization problems. So we are considering minimization of f of x subject to x, but now f is not assumed to be differentiable. So in other words, we cannot apply the gradient method. In fact, all the methods that we have seen so far are for differentiable cases, but it's not necessary that f be differentiable. And a very common example of that which we have already seen is the lasso problem. Right? So in the lasso case, it was actually not differentiable. It was not a differentiable problem, and therefore we cannot apply something like gradient descent there. Now, for non-differentiable cases, we actually need to use a generalization of the gradient. So now that generalization is motivated whenever f is convex. Right? So we do require f to be convex. Now recall that f is convex means that it would satisfy the first order condition. So f of y would be greater than equal to f of x plus gradient f of x inner product with y minus x. So the subgradient, there is a subgradient which is the generalization of the gradient. So the subgradient of f is any g, let's say subgradient of f at x is any gx in Rn such that f of y is greater than equal to f of x plus g inner product of g with y minus x. Right? So this gx is a subgradient of f at x. So subgradient of f at x. So any gx which satisfies this is called a subgradient. Now obviously, if f is differentiable, then gx is simply the gradient of f at x. Subgradient is the gradient when f is differentiable. In fact, this is the only quantity that works here. So gx can only be the gradient, nothing else. But in general, if f is not differentiable at a point x, then so otherwise it is the subgradient is not unique. Subgradient in that case is not unique. And this fact can be observed from a simple example. So let's say that f of x is equal to absolute value of x, right? So for absolute value of x, you can imagine that there is a line that lower bounds it, but that line may not always be unique. So let me draw the general case. So let me draw the differentiable case first. So in the differentiable case, you can see that there is always a tangent at any point for a convex function, and that tangent will always lower bound. So that is the slope of that tangent in the n dimension is the gradient. So that works in the differentiable case. Now in the non-differentiable case, you can imagine that, for example, in the case of absolute value of x, it would look something like this. So this is absolute value of x, and its lower bound, you can find a lower bound on it for any point except at 0. So 0 is the point where it is actually not differentiable, right? And at 0, you can see that g0. So what is g0? g0 would be the slope of the tangent that lower bounds this function. And you can easily imagine that you can have all sorts of lines lower bounding it. So all these three lines, you can see that they are lower bounding this function at 0. So all these three lines are possible candidates of g0. So in fact, you can imagine that g0 now belongs to the entire interval -1 to 1. So any point in -1 to 1 can play the role of g0 for absolute value of x. So in other words, let me just write down the first order condition for this case at 0. So we have that absolute value of y is greater than equal to, and f of x in this case is absolute value of x at 0, x is equal to 0. So that is 0. And then we are saying that it is the inner product of gx, which is any point g0 times y, because x is 0. So we are really saying that this first order condition is saying that absolute value of y is greater than equal to g0 times y. and you can see that it is actually greater than equal to y, and it is also greater than equal to minus y, and any points in between. So it is greater than equal to 0.5 y or minus 0.5 y. So all of those are valid. So this is the idea of subgradient, and in general I can draw this curve in general. For instance, you have a convex function which looks like this. So at this corner point, you can see the point where f is actually non-differentiable. There are a bunch of choices for the tangent, and this entire set is actually called the subdifferential of f at x. So this is called the subdifferential, and this is really a set. This is a set in Rn, and G0 always belongs to this set. For example, this is the subdifferential of the absolute value at x equal to 0. Right? So this is a subdifferential set of the absolute value of x at x equal to 0, and likewise you will generally have a subdifferential at any point where f is non-differentiable. Where it is differentiable, the subdifferential contains only one point, which is the gradient of f. Right? But in general, subdifferential is a set in Rn. So this is a subset of Rn. And if you want to choose a subgradient, you can just pick any point from this subdifferential. So any point from this subdifferential is the subgradient of f. Right? So these are all gx, and this is the point x where the point is differentiable. So if I summarize our discussion of this example, the subdifferential of f, or the absolute value of x, is given by 1 when x is greater than 0. It is given by minus 1 when x is less than 0. So these two are simple. And it is given by this interval minus 1 to 1 when x is equal to 0. So this is the generalization of the gradient. It is a subdifferential. It is singleton at all points except where x is differentiable, where it is an interval in this case. Let us take a look at another example which is non-differentiable, and let's calculate its subdifferential. So let's say that f of x is equal to max over x, f1 of x, comma f2 of x. So this is the maximization of pointwise maximum of two functions, and let's say f1 f2 are convex, so that f is also convex. And then let us calculate its subdifferential. So subdifferential of f at x, let's assume that f1 f2 are differentiable. So f1 f2 are convex and differentiable. So if that is the case, if f1 f2 are actually convex and differentiable, then the subdifferential is clearly gradient of f1 of x for all points where this function takes the value f1 of x, right? So all points where f1 of x is actually greater than equal to f2 of x, right? So at all points where f1 is greater than, actually strictly greater than f2 of x, it is gradient of f1 of x. Then it is gradient of f2 of x for all points x such that f2 of x is greater than f1 of x. But this is not the case that when f1 of x is equal to f2 of x. So that is the point where this function is non-differentiable. So it is differentiable at all the points, but it is non-differentiable at the point where x1 and x1 x is such that f1 of x is equal to f2 of x. So at that point, let us find out the subdifferential. For that purpose, let us consider, so let's say that, let us consider x tilde such that f1 of x tilde is equal to f2 of x tilde. Then let us write down the first order conditions for optimality. We have that f1 of y is greater than equal to f1 of x tilde plus inner product of gradient f1 of x tilde, comma y minus x tilde, and then f2 of y is greater than equal to f2 of x tilde plus gradient of f2 of x tilde, comma y minus x tilde. So I've written down the first order of convexity conditions for f1 and f2. And now let us take a convex combination of these two inequalities. So we will add these two inequalities and take their convex combination. So we have that theta f1 of y plus 1 minus theta f2 of y is greater than equal to. Now note that f1 of x tilde and f2 of x tilde are equal. So we can just write it as f1 of x tilde. You can also write it as f2 of x tilde. It's the same thing. Plus what? Plus it is the g times y minus x tilde. Where what is g? G, or I should say g of x, is equal to theta gradient f1 of x tilde or g of x tilde plus 1 minus theta gradient of f2 of x tilde. Now note one more thing, that this holds for all theta in 0, 1, and further max of f1 of y comma f2 of y, which is actually defined as f of y, the max of these two is always greater than equal to their convex combination, right? So the max is always greater than equal to the convex combination, right? This is simple enough to verify, and this is greater than equal to f of x tilde. F of x tilde is really f1 of x tilde, or you could say f2 of x tilde, plus g of x tilde comma y minus x. So this is really the definition of subgradient, which means that g of x tilde, which we have written here, is a subgradient, and it is a subgradient for any choice of theta, and therefore this suggests that the subdifferential of f at x tilde is theta gradient of f1 of x tilde plus 1 minus theta gradient of f2 of x tilde for theta between 0 and 1. Now we have seen this kind of definition before. This is what? This is really the convex hull of f1 of x tilde comma f2 of x tilde. So you take these 2 points and take their convex combination, convex hull, or really the line joining f1 of x tilde and f2 of x tilde in n dimensions, and that is this set, right? So this is the subdifferential, and in fact you can generalize this for n points, n functions. If you have pointwise maximum of, instead of 2 you have m functions, then it would be the convex combination of all those gradients. And the subgradient definition also allows us to write down the generalized optimality condition, right? So the generalized, if you say that x star is equal to arg min of f of x over x, and we said that the gradient of f equal to 0 is the optimality condition if f is differentiable, and if f is not differentiable, you can simply say that the optimality condition is that 0 belongs to subgradient of f at x star, right? So subgradient definition allows us to make this generalization. It's just saying that 0 is one of the subgradients at x star in case x star is a point where f is not differentiable. Of course, if x star is a point where f is differentiable, then its gradient is 0 is the condition. And finally, we can write down the subgradient method based on this idea. So subgradient method is simply xk plus 1 equal to xk minus eta k g of xk, right? So that is the subgradient method, where g of xk is the subgradient, right? So it belongs to subdifferential of f at xk. So this is the subgradient method. It's a direct generalization of the gradient method. Just replace gradient with subgradient. And generally subgradient methods are slower than gradient. So this non-differentiability is actually, there's a price for that. They're slower in terms of convergence. It converges slowly. So there are various methods of improving those convergence and so on. But to emphasize that subgradient method is one of the very basic methods for convex optimization. Except for convexity, you don't need anything else. For all convex functions, a subgradient always exists. So this is the subgradient method. Next, we will look at faster methods for optimization. So subgradient is the slowest, then gradient, and then there are also faster methods for which algorithms converge much faster, especially for large n. X is in Rn, so for large n, we want fast convergence. So we'll look at some other methods for that purpose.